I'm going to begin today's lecture with talking about building our understanding of the Earth as a system and sort of thinking about where the planet Earth got to where we are today. And one of the sort of building blocks in terms of understanding how the Earth works and putting it in context is recognizing that we have to understand, in what way the Earth actually became the planet Earth that is now. And the fundamental question that led to a lot of the concerns regarding figuring out how the Earth worked was really getting an understanding of how the Earth evolved over time. And really what has been a fundamental question of humanity for quite some time now is understanding the age of the Earth, and leads to a lot of philosophical questions, but as well as having great potential for understanding key scientific endeavors, such as understanding the evolution of life, not just human life, but life throughout the history of the Earth. Has a lot of implication for understanding how climate's changing now, how climate's changed in the past, and leading to a plan of making sure we can understand how those things go. But also fundamentally it allows us to understand the geological processes that influence the planet we live on, so that we can have some perspective of how they might influence life, sustainability, population growth, and all those themes we talked about earlier. So we're going to jump right in, but I have a sort of a general scientific question for all of you, obviously rhetorical given the online nature of the course. But how would you determine the age of the Earth? Now, what are the approaches you can use to actually figure out how old things are and how long we've been here? One of the key concepts that have been developed over geological science, the history of geological sciences, is this idea of uniformitarianism. I'll cover this in more detail later in the semester, but basically the fundamental underpinning to all of our efforts to understand the age of the Earth are an assumption that all the processes that are occurring today occurred in the past at approximately the same rates and the same influence. So with those tenets in mind, that's something that's evolved throughout the geological sciences. But let's just pretend for a moment that we don't even have that understanding. We know how are we going to determine how long things have been going on? I saw someone joined in with an idea of ice cores, and that's an important component. It allows us to look at annual precipitation of ice and allows us to count back a certain number of years. If anyone else has any guesses, I'll try to follow along on the chat room. But some other examples students commonly give me in other years of taught this course are tree rings, right? And both tree rings and ice cores are very useful. They allow us to understand an annual component. They allow us to look back a fixed number of years. And clearly by doing so, we can come to the conclusion, if we assume that trees grow, have an annual growth ring, or ice cores have an annual layering of precipitation, that we can count back number of years. And that's a great example. It allows us to basically record back into the dozens or hundreds of thousands of years through either of those methods. But how else would we get there? I saw someone joined in with carbon dating, and that's going to be an example of a radio dating technique, the fact that certain elements will decay at fixed time constants that we can count and basically get a sense of where things evolved. And that's the right concept, and we'll talk about some of the other components that are tied to that to sort of figure out how we came to be where we are and came to the understanding we have of the age of the Earth. So what I'm going to do briefly is I'm going to move on to talking about the sort of how this science evolved. This question, as I've already alluded to, is as old as time itself. Probably people have tried to date the Earth for hundreds of years. Long before that, people were doing it and thinking about it. But quite frankly, one of the more famous ways, one of the more famous age estimates was done by, in 1650, by an archbishop named James Ussher, who was a bishop in the Church of Ireland. And basically, he did a careful and detailed study of all the biblical and historical sources that referenced the time of the formation of the Earth. He had produced a very hefty tome, which is quite famous, called the Annals of the Old Testament, which said that the Earth formed at approximately noon on October 23rd, 4004 BC. So that's sort of an interesting way, and for a long time it was sort of the way people thought, and it's been accepted as an age for a long time. But you notice the peculiar precision in terms of exactly at noon on that day. But there's a lot of things we didn't know. Okay, and I'm not in any way criticizing his approach in a sense, but I think there's things we have to recognize from a scientific basis that we didn't know in 1650 that we have an understanding of now that better inform our direction in terms of how long there's processes related to it. One of the examples of things we didn't know back then were the fact that we didn't live on a static Earth. That in fact the Earth is a dynamic process with plate tectonics, at least the theory that allows us to sort of understand what's happening now, where the Earth has plates that both move around, but are actually driven through process of recycling, where those plates are subducting into the mantle, being recycled and coming out in volcanism and other parts that move plates around and allow the Earth to sort of recycle itself, which for starters sort of creates its own time increment that we recognize is much longer than one process. Whoever mentioned carbon dating or radio dating techniques in general, we didn't realize that there was things like nuclear fission occurring in the sun's core that produced elements that decay and allow us to get fixed time constants of decay that can be used as clocks, if you will, for processes. And then, quite frankly, at the time, we had a fairly rudimentary understanding of how the various features of the Earth formed. At the time, there was very old theories I won't go into in geological history now, but if you're interested in this kind of thing, there's a long history of folks believing in things like theories you'll never hear about now, things like geosyncline theory, where somehow there was a massive weight put in one part of the Earth, and that caused mountains to build in other places and valleys to form in different places. And of course, now through our understanding of the evolution of plate tectonics, which don't worry, we'll cover that in good detail throughout the course, maybe not necessarily in today's lecture, but we'll certainly know enough about by the end of the semester to be dangerous. We didn't really recognize these factors, and it's really been a continuous evolution in terms of advancing from this approximately 6,000-year-old age of the Earth to where we're at now, based on continuing to roll back different aspects of understanding how the Earth worked. So one of the more famous attempts was the guy named Edward Halley, who suggested that if you divided the total amount of salt in the world's sea by the amount of salt added to the world seas each year, so basically how salty is the ocean, how much salt is coming out of a river to that ocean, you could get the number of years that the oceans have been in existence. And basically his idea was that, through an effort at scientific endeavor, you get an estimate of the rough idea of the age of the Earth. So there's no pressure to answer on chat necessarily, but can everyone take a second to think about some of the problems with that approach? One of the first things that comes to my mind is that you can go out and measure the amount of salt in an ocean. You can measure the salt in a river, but in 1715, as you probably could guess by the name Edmund Halley, he was a Englishman, and his first attempt was to go out to a river near his home that was discharging into the ocean, measure the salinity. I don't expect everyone to know this, but the bottom line is there's different amounts of salts and dissolved elements in every river. So for starters, some of the problems with the approach is that how can you tell what the flux of salt would be on the whole ocean, particularly in 1715? And reality is that it varies, and it's a very hard thing to do. The other component of that is that as I mentioned earlier, we didn't really have any understanding of plate tectonics or the fact there are cycles in the dynamic history of the Earth. And as a result, at that time, he was fairly left to assume that the ocean was basically a bathtub that was slowly filling up with salts that were being brought down by rivers, and that he could use that amount of salt accumulation to determine how much time had elapsed since the Earth formed. But of course, now understanding plate tectonics and the fact that the Earth is sort of continuously seeing subduction and formation of new plates, we would recognize that one of the biggest problems of that approach is that there's been cycles which the ocean's overturned and salt deposits are preserved in that sedimentary records, and new oceans are formed. So in essence, best case scenario would have given us an estimate of how quickly salt cycles in the history of the Earth. And in fact, we know now that that's really not even necessarily along those lines. So the first, one of the later, was considered more serious scientific attempts to measure the Earth's age was fall in the same century in the 1770s by a Frenchman, Buffon. And basically, his idea was basically applying physics, and it's now we'd call this black body radiation, or black body physics. And what he would do is take spheres of different sizes and materials, heat them up until they glowed white hot, and then estimate the rate of heat loss by in his case, by touching them, and I make the joke here, presumably very delicately first, as they cooled, and looked at the rate at which different bodies would cool, and come up with an estimate of how we could estimate the age of the Earth by basically making the assumption we could go to the Earth, we could measure the heat flux that's occurring there, and we could assume it behaves like a constant black body radiation, a source of black body radiation, and get an age. And Buffon was quite, along with several other scientists in that generation, were quite famously going to every deep coal mine they could find, going down to the bottom of the coal mine, measuring the temperature, and basically using that by extrapolating the idea of black body radiation to state an estimate of time. I saw someone ask what the spheres were made of, and I think that, from what I understand, most of them were metallic. I presume some sort of iron ore, but I think he, over the course of time, he did this with things ranging from metals to rocks, and when you actually get to black body radiation to a first order at higher temperatures, they kind of approach a sort of a norm. The issue with this, and let me just take a step back here. This theory led to a lot of potential initially, because people were savvy enough to recognize as you went deeper into these mines or into caves, the temperature got hotter, and as a result, this was actually considered a mark of success, because it basically pushed the age of the Earth back from about 6,000 years to something in the in the few hundreds of thousands of years, which is at least in the right direction. So, based upon the different range of spheres that he heated up of different compositions, he came up with an age for the Earth between 75,000 years and 168,000 years old, which of course now we recognize is still, many orders of magnitude too young. But the time was actually considered to be an incredible, audacious, if you will, result to suggest. As I said, we know now that's a pretty wild underestimate, but at the time it was considered quite radical. And Buffon, as a Frenchman who lived in a largely Catholic community, was threatened with excommunication for expressing it, and he pretty much immediately, considered himself a practical man. He apologized at once for his thoughtless heresy, and cheerfully repeated the assertions throughout the subsequent writings, meaning that he would publicly state that he was a moment of the devil's influence and thoughtless heresy, but actually would sort of go around to a lot of the pubs and speakeasies, and that's not exactly the right word, but I guess pubs more so, and bars, and sort of discuss this with the scientific community at the time. So he never really gave up on this theory, and ended up having quite a lot of influence in terms of how people thought about the approach we could use to get some estimate of the timing of the Earth's history. Before we move on, just in terms of thinking about processes like the fact that the Earth does have heat in it, does anyone know what the component we didn't really know about at the time that sort of made his interpretation sort of grossly underestimated? Again, I don't necessarily, I'm not going to expect everyone to write it in chat. I'm just giving a moment for everyone to think about it. But what we didn't know about at the time, what aspect of the fact that the Earth had heat that increased at grading depths was missing from the scientific knowledge at the time that didn't allow Buffon to make an accurate estimate of using black body radiation? And I'll just answer my question to move along here. But basically, he was not aware of. Okay, I see some folks are coming in here. The molten core, it's a great example. There's something called latent heat, the amount of heat that's incorporated into the Earth's core rather, and mantle from the time the Earth was formed, which has heat that's slowly cooling down. That kind of could be maybe incorporated. I see someone saying layers of the Earth, which is the fact that not all of the Earth is of the same material. So using one type of material wouldn't allow you to get a black body radiation temperature profile. And the other component that I want you to think about is the fact that we didn't know about radiation. We didn't know that there were elements in the Earth's core, mantle, and Earth's crust that were actually decaying and releasing heat during the process. And we'll come back to that a little bit later, but all of those processes sort of allowed him to, or not allowed him, but led to a scenario where he sort of assumed the temperature was started at the formation of the Earth and was decreasing, where in fact, if for those of you who might have learned this in another geology class, most of the heat that keeps us alive on planet Earth doesn't actually come from the sun. That radiates through the clouds and is captured by greenhouse gases and kind of regulates surface temperatures. but below about 5-10 feet, much more shallow in certain areas, the temperature of most of the Earth is actually regulated by heat that's produced by radioactive decay within the Earth's crust, mantle, and core, and that, as a result, gives you a very different flux on heat. So if you measure, this is an aside, I won't test you on this. If you got to measure the surface temperature of any area and look at the heat flux, it's more tied to how much radiation is being produced by radioactive decay below you than it is about the age of the Earth itself. So in essence, he was wrong, but led us down a path that was useful. But importantly, the goal I'm trying to make here is that by from 1650 to 1770, we've gone from 6,000 years to 170,000 years nominally, which shows a great deal of advancement in terms of our understanding of how this would work. Clearly, through a lot of various experiments and a lot of scientists who went down this path, I'll skip ahead, but based on using Buffon's assessment of heat flux and going into deeper and deeper mines throughout the Earth, they actually had estimates pushed back into the few millions of years by the 18th and 19th century. So by the middle of the 19th century, most educated, learned people throughout the Earth sort of assumed that the Earth was a few million years old. Some people would even dare to say, tens of million years old, but probably most folks accepted it wasn't much older than that. Even by then, before plate tectonics, before we had a very good understanding of geology, there was a growing idea that maybe the Earth had the ability to rejuvenate itself. We started to understand things like volcanoes and understand things about earthquakes and the Earth moving. And it was really in this time frame where people started to assume that this wasn't just a sort of a higher power. God was mad at them and therefore the volcano erupted, that there was actually something happening on planet Earth where things were moving, which allowed people to think about the idea there might be cycles, and came up with the consensus in the scientific community that the age was probably even older than we expected, perhaps in the millions or tens of millions of years old. So here's our friend who appears in a lot of different places during the time, middle 1850s. That's Charles Darwin. Of course, he's famous for the origin of species and talking about evolution. But he had also been very much an active geologist for most of his career, always making observations about geological processes, geological formations, and geological, different field observations, really tying back to his search to understand evolution. And he quite famously, in a very detailed study, evaluated all the processes that led to the area of Weald in southern England. And he looked at various coal mines and outcrops, and looked at things like the things that are called folds and faults, where the different plates have moved around a little bit. And basically, by assuming that everything was flat, which is actually a fairly novel idea at the time, there was a geologist named Sutton who had basically recognized that had come up with the idea that sedimentary rocks are deposited flat, and therefore changes in that flatness can give us some idea about how the Earth evolved. He came up with an astounding calculation for the 1850s, which said there was about 306 million years had elapsed between the formation of the Earth, based on the fact that southern England had evolved, over that amount of time. On the positive side, in terms of getting to the right answer, Darwin's approach was again following on from Buffon, leading to a very detailed scientific approach to evaluate the age, and it was in the right direction. Those are the positives. The negatives are, it wasn't entirely clear what all assumptions he made in his assessments of the calculations, and as a result, it sort of was largely sort of overlooked. But again, was remarkable at the time for being so different than what had come before it, and flying in the face of the wisdom of the Earth couldn't be more than a million or a few million years old. In essence, despite the fact that to this day we still think about Charles Darwin as being a contentious, controversial evolutionary, revolutionary in terms of advancing theory of evolution, I think most folks have come to recognize that he was on the right path, and also, despite the fact that was received so much attention at the time, this theory that the Earth could be 300 million years old, even though now we know it's much older than that, proved so contentious that Darwin actually withdrew it and withdrew from the literature entirely. So I guess he had a lot more confidence in evolution than saying the age of the Earth could be that old at the time. So I like this quote from Darwin, which says, And you can see, looking at this picture, why he says this. If I really have as bad an expression as my photograph gives me, how can I have one single friend? Is surprising, which I assume he's talking about his sunny disposition there. But the Darwin was quite a character in a lot of different ways. So still, we have this idea now in the 1860s that maybe we have something that's 300 million years old, but wasn't very well founded or very well documented how he came to that conclusion. Ironically, just for anybody who's actually interested in this, the geological units in that part of southern England are actually on the order of about 380 million years old. So in essence, I have no idea why he got an age that was so close, and he certainly was nothing that we could verify or reproduce now. But in essence, he wasn't, ironically, that far off. So by the close of the by 1900. Depending on which text you consulted or which geological expert you asked, most people came to the interpretation that there was a lot of time involved, allowing us to experience the amount of evolution and geological processes. Darwin is certainly an influencer, if you will, in terms of that. But still, there was great debate. Everything ranging from top well-respected experts at the top universities in the world at that time would still put a range between 3 million and 2.4 billion years since the age of the Earth and the dawn of complex life, and many others put ages between there. These are just a collection. I don't cite the references here, but these are a collection of ages that were put out in prominent textbooks by faculty members at places like Yale and Oxford and things like that, who are certain they understood how the age of the Earth had formed, or the age in which the Earth formed. And for example, this even though I show these numbers all going in the right direction, even as late as 1910, one of the most respected geologists, George Beck at the time, put the age of the Earth as little as about 55 million years, which gives you the idea that not only 120 years ago we still had an incredible amount of debate about the age of the age of the Earth, and a lot of misunderstanding of factors and approaches that allow us to get to the actual answer. So for whoever kudos to whoever came up with the idea of carbon age dating, but that's very much along the right path. It was really until about the turn of the last century where we had a very accidental discovery of radiation at the time, which led to the idea that we could actually get a clock to understand the timing of the formation of the Earth, something quantitative rather than qualitative, to guess at how long it would take life to evolve and how long it would take fossils to evolve. And for those of you who don't know, it's an incredibly important discovery, but an entirely accidental one, as many serendipitous scientific discoveries are. But it was actually in Paris in 1896, where a professor named Henri Becquerel, which Becquerel is still famous for using the name. The Becquerel units are still famous for and commonly used for determining the amount of radiation that occurs. He accidentally, maybe some would say carelessly, left a packet of uranium salts, which were recovered from a pitchblende ore deposit in France. And he just basically accidentally set it on top of a photographic plate in a drawer in his desk. And this is actually the image. You can see the discoloration where basically the light source was imprinted on the photographic plate, and that's where he first came to the conclusion that perhaps there was some sort of radiation occurring. So when he removed the plate to use it, he observed that the salts had sort of burned an impression on it, realized it had been exposed to light exactly where the salts were occurring, and he made a really impressive deduction, which was really fundamentally changed the course of humanity and science at the time, which were that the salts were emitting some rays of some light. As professors too commonly do, he sort of just turned this project over to his graduate student to figure out what it was. And hopefully many of you have heard the name Marie Curie before, who very famously was the one who worked out radioactive decay and unfortunately also ended up succumbing to radiation poisoning before she died. But what she spent a lot of time working on was finding that certain type of rocks, particularly rocks that were uranium rich, sort of poured out a constant and incredibly impressive amount of energy. But that also, even though it was constant, it constantly decreased through time, depending on which particular type of rock she's looking at. And really what she was able to work out throughout her graduate studies and her professional career was this realization that there was a decay of radioactive elements that could allow us to get some time component of age. What wasn't really worked out at that time was that the rocks were converting mass into energy. This eventually becomes Einstein's theory of relativity with E equals mc squared, where when mass can be converted, mc squared can be converted to energy, and that's where all this incredible volume or incredible amounts of energy were being generated by reactive decay. And at that time, she did dub the concept of radioactivity, which is stuck till today. And of course, Marie Curie is a Nobel Prize winner and a very incredible influencer at the time, and is more than a century later is one of the most important discoveries we've sort of ever discovered. So it was really later moving from Paris to Montreal at McGill University. Ernest Rutherford, who again became a Nobel Prize winner, was really the one who sort of got involved with this, got really interested in these new radioactive materials, and he focused more on thinking about the amount of energy that was built up in these atoms and in these incredibly small amounts of atoms, and started thinking about this in terms of realizing that this decay process changed our understanding from Buffon's efforts in terms of thinking about things like a heat budget. That he recognized that, in fact, Buffon might have had a really novel idea, but was sort of wrong for reasons he didn't understand, which at the time, which were the fact that the heat was actually being tied to radioactive decay, and that decay process, given the fact that it occurred at a constant rate, could be used to put an age on the Earth. He sort of quickly worked out a lot of the aspects of the half-lives of decay constants, recognized that you could go from uranium to lead in over some period of time. Obviously, these can be very long periods of time, but he's the one who sort of took Curie and Becquerel's discovery and worked on developing sort of the radio dating clocks that we're going to talk about. So I'm just going to briefly cover this. Hopefully it's a review. If it's not, don't worry. It's not all the questions I'll ask you in the exams are similar to what's on the worksheet for this week. I just want to make sure we cover the basics. But just to remind everyone, all of us, all the buildings, rocks, computers, everything we're dealing with, everything you can think of, it's all composed of atoms. So all matter is composed of atoms. And I'm going to cover what these are, just to remind you as a refresher. So atoms are basically largely, the majority of them are stable, very long-lived. I don't even know what 1 times 10 to the 35th power is, but well beyond the length of our solar system. For the vast majority of elements, they're called stable isotopes, if you will, but most isotopes, in fact, are stable. And for perspective, these things are persistent. They're neither created or destroyed. They've been around forever, and it's a philosophical fun to think about, but clearly every atom in your body has certainly passed through multiple stars, probably many living beings, and been part of, probably an estimated millions of beings based on the amount of recycling of life and air and things like that. So, from a philosophical perspective, we won't get into that here, but the key thing here is matter is not created or destroyed. It's basically constant, although it can be converted along those ideas of a small component of the atoms that are radioactive can be converted to between mass and energy, which we'll talk about as we go on here. For perspective, just to remind you, these atoms are incredibly small. You can think about 500,000, 500,000 of these atoms lined up end to end are still smaller than the average human hair, which is give you a perspective just how small these are. Key components here is that the atoms are made up of 3 fundamental particles. There's of course a greater understanding every generation in terms of what physical particles are parts of these components. But for our classes, for this purpose, we're going to stick to the 3 elementary particles, and those elementary particles are going to be protons, electrons, and neutrons. From the simplest perspective, protons are positively charged. They're relatively massive. Most of the numbering in the periodic table is based upon the atomic mass unit, or the idea that a proton largely makes up a mass of about 1. Electrons, in comparison, are negatively charged and have significantly smaller masses than protons. And neutrons, if you want to think about them like this, they are present on Earth or in the universe wherever a proton and electron are combined. You literally, a 1 proton plus 1 electron means a neutron with slightly more mass than the proton, but a neutral charge. So those are the three sort of elementary particles. Again, protons positively charged, relatively similar mass to neutrons. Electrons negatively charged, very low amounts of mass. And the neutrons, where the two are combined, so by definition, the mass is slightly greater in neutrons than protons alone. Back to, this might be a flashback to high school chemistry, perhaps, or physics. But the key thing to remember here is that basically protons and neutrons are in the center, and electrons have an orbital that migrates around them. And don't worry, we're not going to go much deeper into this at all. In fact, pretty much after this lecture, you'll be done hearing about protons, electrons, and neutrons, but the basics are important. So again, protons and neutrons packed in the nucleus in the center, electrons spin around them in some orbital, or at least that's our orbital theories we'll talk about. And the key thing to remember is that the protons, the number of protons, is what tells you something is a particular element. 1 proton is hydrogen, 2 is helium. We're not going to have any exams on the periodic table. Don't worry about it, but the basics are important, and I want you to make sure you have the exposure to them at the very least. So atom with 1 proton, hydrogen, helium, 3 is lithium, and on it goes. And then the key aspect here is that based on the fundamental balance of charge in these nuclear particles, there's always a balance in the number of protons and the number of electrons. The difference here, which is really relevant, is that the number of neutrons, which again are more massive than protons, so they change the fundamental mass that's in this configuration, can vary. And that number of different neutrons that can be in an element is what actually gives life to the idea of an isotope. The fact that different in a given atom with one proton is hydrogen, but depending on the number of neutrons, we can actually have different isotopes. In most cases, there's a few isotopes that are stable and behave just like we think of atoms, and they make up the vast majority of the mass of the elements. And usually there's a relatively large number with a very small amount of atoms that have varying number of neutrons or isotopes that make up the potential package or suite of isotopes that can be reacted to decay. And again, don't get bogged down in this detail, and most of this is much more detailed than our understanding of this probably needs to be. The key thing here is that a number of different elements in the periodic table will have the same protons but a differing number of neutrons, and then that'll create an isotope. And only some of those isotopes will actually be available for radioactive decay, which we'll get to here in a second. So just to again give you some perspective, this picture, as I think here in a second, is not to scale, but the atom of a nucleus is packed with protons and neutrons, very dense amount of mass inside a very small area, and the electrons, of course, are they're not really in direct orbitals, but are spinning around these charges. But again, most of the area in a atoms are largely empty space, and there's an incredible amount of energy that can be derived from pulling these things apart. So when I ask this question, is the diagram correct? If I would give you this question on an exam, I would hope that you would say no. One of the most obvious thing is it's not scaled correctly, and secondly, electrons don't go in these finite orbitals; they just sort of in a cloud around the nucleus. So moving forward, I'm not going to go into this in much detail, but you can just think of these electrons as being everywhere around the atom, but in general, it's going to be at a fixed distance from these. And the famous scientist that led to this is a guy named Niels Bohr. He won the Nobel Prize in 1922, and sorry, this got cut off here, but was one that really developed a lot of these ideas. Niels Bohr, in addition to winning the Nobel Prize and basically coming up with this model for how an atom and a nucleus and electrons work, he was so excited by this work he won the Nobel Prize for. He actually postponed his honeymoon to write a paper on quantum theory to explain this to the scientific community, and it still has lasting impact almost 100 years later today. So moving to what's important for us in terms of getting to the age of the Earth is that we can recognize that there can be different isotopes based on the different numbers of neutrons So this is a carbon atom here again, just a flashback to high school chemistry. 6, it tells you how many protons. And notice that no matter which carbon you have here, it'll have 6 protons. And this number up here tells you the total mass, right? And that mass basically difference tells you there's an extra neutron there. The key aspect here is that, which we won't cover much in this class right now, is that there's also an additional form of carbon called carbon-14, which has too many neutrons, becomes unstable, and actually has radioactive decay that we can use for radio dating of carbon-based things. The key aspect that we're going to utilize to get back to the age of the Earth here is the fact that that every element that's radioactive that we know about in the periodic table has a half-life. They vary depending on the type of element. For example, here I show you uranium-238 has a half-life of about 4.47 billion years. So that's about the age of the Earth, right? Give you a sense, it means half of the amount of original uranium will decay away after one half-life. In uranium's case, that'd be 4.47 billion years. Or for uranium-235, which is 704 million years, the half-life would be shorter. The key thing here is that does mean the uranium-235 will decay away faster than uranium-238. But the important aspect here is that this graph showing 100% of the original amount of an element, half, quarter, eighth, 16th, and then occurring along this half-life is called exponential decay. And that curve holds true for every single radioactive elements out there, with the exception that the half-life of various radioactive elements differs. Give you an example, in my lab, downstairs, and where we're in Mendenhall Laboratory, where we normally have this class, I specialize in measuring an element called tritium's decay to helium-3, which happens about every 12.43 years. So these things can be, almost instantaneous. They can go over a few years, and many of them have billions of years longer than uranium. The key aspect here is that if you know how much was there initially, and you can measure how much of either the new element has been formed or how much of the old element has been lost, you can use this clock and a half-life to get an age. Okay, so the key aspect of radioactive decay is the nucleus becomes unstable because of an imbalance in the number of neutrons. Usually, too many neutrons in the nucleus, but it can go both ways. And basically, when that happens, you'll see that the stability of the atom is regained by basically emitting some form of radiation. That can be it can come in one of 3 different ways, but effectively what I want you to remember here is a key part of this is that means when we're emitting radiation, we're going to emit some light, some heat, and sometimes some mass. Don't worry about the nuances of which alpha, beta, gamma at all. I'm going to cover them so you have it for those of you that are interested and so you have a background on it, but the key thing to remember here is light and heat are a constant that's being released by any radiation. The 3 forms, which are called alpha, beta, and gamma, are basically increasing the amount of light energy but decreasing the amount of mass that's going to be transferred. So in alpha, you're actually going to be kicking out sort of 2 protons and 2 neutrons, or a helium molecule, that'll get pushed out of this. The most common type of technique that was used early on was using uranium decay, and that decays to lead and helium. And this led to the idea that alpha particles, a helium molecule, that gets kicked out of the uranium. For those of you who are interested in this, haven't already fallen asleep in this discussion of nuclear particles and radioactive decay, is the fact that helium is often the product that's broken down and lost as an alpha particle because it's so stable. It's a very much, with 2 protons and 2 neutrons, is almost as perfectly stable atom as there is on, it is physically, and as a result, it's a particle that sort of commonly breaks down very easily in a lot of sort of alpha decay processes. So you can look this up in more detail. I'm not going to test you again on alpha, beta, gamma, or anything like that. Light and heat, but I want to have a sense of this. So as an example, and this is an important one, I chose this one specifically because it's very commonly used to understand the age of the Earth, is that uranium-238, for example. So again, all the uraniums will have 92 protons. 238, that difference tells you the number of 92 protons. 238 tells you and the different isotopes, 235, 238 tells you the number of neutrons. It'll decay to an alpha particle and decay product in that decay chain. I'll let you have a second to calculate this, but again, the key thing here is light and heat are going to be emitted. And if you do the math here, if you have to give up 2 protons in order to make the helium, an alpha particle, the helium atom, that means you're going to have a mass of a number of protons of 90. If you have to give up 4 mass units, that's going to give you a 234. And for those of you who have done the math at home, that'll read a 234 over 90. And if you look that up, that'll be 90 defines it as a thorium. So that's the first step in the decay process for alpha particles. Key thing, and I know this is one of the lectures I always am a little bit uncomfortable giving because there's a lot of detail and I worry I lose people who just aren't interested in this in great deal. But the key thing I want to make sure everyone comes back to and focuses on here is that the fact that radioactive decay occurs and that it occurs at a steady rate with a fixed half-life, that's the key parameter which allows us to use this technique as a clock to test the age of various materials. We're going to clearly come back to the idea of trying to use this to test the age of the Earth. But for the person who mentioned carbon dating earlier, it's exactly right. For different materials that incorporate carbon-14, this exact steady decay at a constant half-life allows us to get the age of different things such as scrolls or different types of matter that's in for example forest fires or different things where we can put an age and when things occurred. I'll lead with the punchline here and to say that this process is largely makes up largely the field of geochemistry, where there's a whole suite of different people in geology departments all over the world who have what's called mass spectrometers, and they basically measure, knowing the half-life of these things that are determined independently. They measure various samples of water, rocks, gallstones, even, you name it, we can do it and get the age of different things. My lab actually focuses on this very directly, and we focus on measuring how old water is based on using some of these clocks. I was giving the example of gallstones, how long it takes different things to form. So it can be biological, it can be geologic, it can be water, it can even be very historically focused, looking at old scrolls or legal documents to determine when people had written things like this. And I don't do this kind of work, but a lot of people actually use this to look at things like artifacts for cave dwellers, and they started actually putting, writing evolved. And the applications are literally innumerable you can use this test for. But getting back to our original topic, which is how do we figure out how the Earth works and how do we figure out how old it is, one of the first materials that Rutherford focused on was actually using some of that original pitch blende that was accidentally led to the discovery of radiation. And what he did by looking at the clock of how much had decayed and knowing the half-life as best he knew at the time, which we always make that measurement better, he basically came up with a very robust, scientifically focused age of the Earth to be about 700 million years, which at that time was older than the oldest scientifically based evidence by Darwin, which of course he actually retracted, but was much older than most people were really prepared to conceive of as the Earth. I always found this fact to be interesting. Maybe none of you will, but apparently for the average human brain, most people can't actually can't really totally conceive of what 1,000 of something means. So, for the human brain to actually think about millions, let alone 700 million, quite frankly, it took a long time for people to accept that, and it's not entirely clear that even geologists who get used to thinking about really long periods of time can actually conceive what that truly means. So it's kind of an interesting thing to think about. So even at that time, early on, with still some great uncertainty in the actual half-life, which again, we get that number better and better and better to more decimal places every year. The age was 700 million years old, and that took a lot of effort to get that value accepted. Many folks really couldn't quite conceive of that or wouldn't believe that. And what this led to, effectively, was almost a generation or two of geoscientists, physicists, and chemists who worked on developing new techniques, new mass spectrometers to measure and count these decay products, looking for the right idea of the right samples we could get to understand what the age of the Earth is. And with really even with that idea in mind, 700 million years, some of the greatest scientists, many Nobel laureates, still it took almost a generation, about 3 or 4 decades from the 19 teens, the 1920s, till after World War II in the 1950s, before we actually had any acceptance that the age of the Earth was, in the billions of years time frame. My academic great grandfather, if you will, my PhD advisor, was a man named Harold Urey, who developed a mass spectrometer, and he was one of the people who largely did a lot of this work. And he's credited with basically pushing the age of the Earth back from about 700 million years all the way back to about 4.3 billion years in the course of about 20 years of ongoing work. So, to give you perspective, this was a long time before we got to where we know now. In essence, the application wasn't just focused on getting the age of the Earth. A lot of people initially actually focused on what one of you suggested, which is carbon dating. And initially showed a lot of promise. It's still widely used today for looking at things that are living or things that included something that's living, such as paper. But basically, for the age of the Earth, what people came to realize is if you went out into most rock deposits and you looked at the carbon-14 age in those rock deposits, because the half-life is relatively short, 5,600 years, basically all the coal deposits and all the shale deposits and all the rocks that had carbon in it that people looked at, they kept getting the same answer, which was that it was at least older than 40-some thousand years. So nowadays, we do use carbon age dating widely, again, for a lot of different things. But in terms of coming up with the age of the Earth, what it really convinced people of is that the age of the Earth was at least more than 40,000 years old, which most people have sort of already agreed on. And the key reason here is that after about 8 half-lives, only 1/256th of an original radioactive carbon, in this case, or any element remains. So the key thing here when we actually start thinking about determining the age of something, particularly the age of the Earth, is that we have to recognize that you have to match it's sort of an iterative process. People call this pigeonholing, where you have to basically get data points, different areas, and you figure out what questions are still possible, and you keep making that possibility smaller and smaller. So what people were forced to do was they examined all these rocks with carbon age dating, and they found that it was older than 40,000 years old, or older than 60,000 years old if you use the most modern mass spectrometer. Then they would go on to another form of radio dating, for example, looking at the uranium decay series, and they'd find ages in that particular technique, and they recognize, okay, we know the age of the Earth isn't older than X, Y, or Z, and people would slowly sort of build a consensus. The age of the Earth was in smaller and smaller windows. But point being here is that although many people think of radiocarbon dating, which is a great technique, it really didn't provide much value in terms of determining the age of the Earth. So I'm gonna basically, I think this is a natural break, if you will, in terms of leading to coming back to using a different technique, uranium and lead isotopes, to determine the age of the Earth. So rather than continuing on with the lecture for today, I'm going to pick up here on the lecture on Wednesday. And I just have a few notes on the class. One is that I'm still having an issue with getting the videos and the worksheets to post at the time I want them to, and also with the video posting. I'm going to work that out soon. I apologize that's happened, but I will say that I think as of this morning, all the lectures, or both of the lectures that came before this, are online in both the video and the slides. So the slides are under the files under lectures, and the place again where the videos are going to be presented are under the modules. So module lecture 1 and 2 both are there with video and audio for all of the course. It looks like everyone did very well, and broadly speaking, everyone did very well in the worksheet. Everyone who participated was able to get most of the questions. If you are okay with that format, you'll be very happy throughout the semester. And again, the worksheets are meant to keep you engaged in the class and moving forward. Makes about 40% of the grade, and the second worksheet was posted. For some reason, it was supposed both the lectures and the worksheet were supposed to post at 5 p.m. on Sundays. It happened at, I think, around 9 p.m. But it is there. So the worksheet 2 is posted. Again, it's due by the end of the week on midnight on Friday, and it's all still the same process. You can go on, take it. If you get something wrong, you have another chance at it, getting it again. but all the answers are actually in the worksheet or in the lectures throughout the class for the week. So lectures are already posted, and all the answers, if you want to go ahead and get them, they're there. But it probably makes sense just to sort of go as you go, fill in the answers as we move along. I see someone mentioning here they don't see the modules on the Carmen tab. If you look on the left side, it's it's a number of things down. It's kind of towards the middle of the list where it says modules. I will take a screenshot of that, put an arrow on it to show everyone where the modules are, and I'll try to email it out in an announcement shortly after class. But plenty of time to get caught up. We don't have a quiz for a little while. If it's not on the module, I will make sure it gets there. But I'm seeing someone saying it's not posted, but I'll make sure that it is done right after class if it's not there. It shows on mine, maybe I posted it but didn't publish it. I apologize for that, but I'll get that sorted out immediately after class. I apologize again. So with that, I'll let everyone go. If you have any questions, send me an email. Certainly, if by the end of the day today, the module 3 lecture doesn't show up, I'm not trying to put the burden on you, but somebody ping me and I'll make sure it gets sorted out. It should all be getting there within a few hours now that we have it sorted out. So, all right, thank you very much for paying attention at home or for reading, for listening to this whenever you got a chance. Hope everyone's doing well, and I'll see you all on Wednesday.